Okay, we are off to chapter 2. Last time we did chapter 1. And in chapter 1, we kind of talked about scientific notation, how to properly write that. We also talked a little bit about chemistry, and more importantly, we talked a good amount about using your calculator correctly, which is half the battle sometimes. So in chapter 2 here, we're going to talk about measurements. We're going to talk about significant figures. We will also talk about conversions and what's referred to as dimensional analysis in this chapter. And we will finish up, I think, talking about some density at the end. So let us get obviously into this. So measurements are really important in chemistry, and it's really important that you do take proper measurements. And when we talk about proper measurements, there really should always be units associated with a number. So, if I wrote, 3,000, and that's pretty much all I wrote, there's really no unit to give us a frame of reference for really what that number means, right? It could mean I got 3,000, donuts, which wouldn't be bad, I suppose. Or I have $3,000, which would be probably better, I imagine. And, so you do need to make sure that always when you take a measurement, should always have the number, and we'll talk about taking it to the proper number of digits. And you should always have the unit, as it does give, again, everybody sort of a reference point as to what that value really means. So when we talk about units, there's really a couple types of systems of units that we commonly come across. For the most part, people sometimes call it the English version of units or the US version. And that's the one, obviously, we use here, like, degrees Fahrenheit, inches, feet. And pretty much everybody else uses the metric system, like kilograms, grams, all those type of things. And obviously that could create a lot of problems as the world sort of got smaller. People started doing business. Some people are on sort of the English unit. Some people are on the metric unit. So there could be a really troublesome sort of situation that could occur. So in like 1960, they had a big conference on weights and measures. Sounds like fun. And they got together and they basically came up for sort of chemistry and science, sort of a standardized set of units that everybody uses. And that is oftentimes referred to as the SI units, or the International System of Units. And for all intents purposes, it, pretty much is kind of based off of the metric system. So it's very much based off of the metric system. So a lot of times in chemistry books, you'll sometimes hear like the SI unit for mass is kilograms, or the SI unit for temperature is Kelvin and stuff like that. So that's sort of the standardized unit that's typically used in, like I said, chemistry or, science in general. And like I said, it really does sort of go a little bit towards the metric system more than sort of the English system that we typically use. And here are some of the basic SI units for different types of measurements that you make. So it's really important when you do take a measurement, when you report something, when you go ask like your lab instructor or something like, hey, this is my units I got, that you're really talking about the right thing. And what I mean by that is typical units of volume are liters, are cubic meters. Typical unit of length are meters, in both sort of the metric and the SI system. For mass, grams and kilograms for the SI system, although most of the time in the laboratory, we do kind of use grams on the balances and stuff like that. Temperature for the SI unit is Kelvin, and that is a unit of temperature that we use a lot in chemistry. Pretty much every single chemistry formula that has anything to do with temperature, pretty much it needs to go into Kelvin in terms of the unit. And most of the time it'll go from degrees Celsius to Kelvin. And we'll talk about how to do those conversions as well in this chapter. And time is seconds in both of them. So it's really important when you say something like, my mass was 35 milliliters. you should understand that that's incorrect because a milliliter is a volume and a mass should be something like grams or kilograms. So you want to make sure you do understand sort of the relationship between the type of unit and also sort of what it means. So let's talk a little bit about volume. Volume is the space that's occupied by a substance. It's measured in units of meters cubed as the SI unit. Now you might be wondering how we get there in terms of, meters cubed being a volume. I would say that probably the most common sort of volume that we see are these two units here, which is liters and milliliters. And the relationship between those two is there is 1,000 milliliters in 1 liter. And that is 100% a conversion. You use a lot in chemistry, converting milliliters to liters and vice versa, sort of backwards. So that is for sure a conversion. Now, a cubic centimeter is actually the same thing as a milliliter. They are basically a one-to-one relationship. So how we get there is actually a lot of times in solids that are cubes or something like that. We actually could take 3 different measurements. So if we measure the length times the width times the height, and we measure each of these in centimeters, which is a length measurement, we would take centimeters times centimeters times centimeters. And when we multiply all those together, that gives us cubic centimeters, which is a volume. So any type of length measurement for the most part that has been cubed is a volume measurement. Each of these individual measurements here, these are all length measurements. So those are all individual length measurements, but if you multiply them together in a cube type situation, you will get the actual volume. Another way cubic centimeters are sometimes represented is with a cc to stand for cubic centimeters. Like give that guy 5 cc's of this or something before he dies, right? So basically 5 milliliters is what they are talking about there. One very common equipment that we use to measure volume is a graduated cylinder, which is that guy there. And typically when we do take readings of a liquid in a container, like a graduated cylinder, we typically will see the curvature of the liquid. And that curvature of the liquid is what is known as the meniscus. And you should always read from the bottom of the meniscus, because what is happening is actually the solution is more attracted to the walls of the container. So what ends up happening is the sides of the solution in the container start to kind of rise up the sides of it, because there's a much more attractive force between the container and the liquid than the liquid in itself. So you get this kind of U-shaped meniscus that occurs. But when you get to the center, that is truly where the liquid volume is, because it's not really affected by the sides of the container, so it doesn't rise or anything like that. So that's why you should always read from the bottom of the meniscus when you take a volume measurement. So as I said before there, 1 liter is 1,000 milliliters. This one does pop up occasionally along the way there, which is the 946 milliliters is 1 quart. So that is a sort of a conversion that does pop up a little bit along the way. But definitely 1,000 milliliters is a liter. A cubic centimeter and a milliliter are the same thing. Those are all things obviously you should know, because they do happen a lot. Any questions on that? So again, here are some of those relationships, and that should be quart. And once again, that is definitely an important one. Now, typical length measurements are typically in meters, very common as well. Centimeters is used a lot. Millimeters is used. Kilometers is used. But we do use, as we will talk about here in this bit, a prefix to kind of change some of these guys, these metric sort of units. But meters definitely, there is 100 centimeters in 1 meter. So that is a conversion that's used a lot along the way. When we look at inches and centimeters, 1 inch is exactly 2.54 centimeters. So that is something that is the difference between an English unit, which is inches, and the metric unit, which is centimeters. So that is used a lot. So I would say these couple here you should be familiar with. You'll probably see them. I don't know how much of these you'll see, but they may show up. But definitely those ones and boxes do tend to show up a good amount. Now, mass, when we do a process of weighing something, that is what is referred to the mass of an object, and that's the quantity of matter or material it contains. We do use, for example, an electronic balance, which, by the way, whenever you use anything that's electronic and has a digital display, you should always record all the numbers that are there, because that's why they're there. They're kind of important. So always on a digital thing, you should record it. I would say the SI unit is kilograms, which we do use a lot, but mainly we do, if we're sort of doing an experiment, we will get the mass in grams as a very common unit. And once again, the relationship between those two, 1,000 grams is a kilogram, is a relationship that we use a lot. Now, there is a difference between the words mass and weight. Mass is really independent of the force of gravity, while weight is dependent on the force of gravity. That means that if you weigh yourself here, you will weigh different here than if you weighed yourself on the moon. But technically your mass would sort of be the same in both places, as is independent of the force of gravity. So it is really important that when you do the process known as weighing, which is why people sometimes will call it the weight of something, when you do the process of weight, we do refer to it as the mass in chemistry. So you should refer to it as it's getting the mass of the object, and not that you got the weight of the object or anything like that when you do it. So the main difference between those two, like I said, is mass is independent of the force of gravity, while obviously weight is dependent on it. I would say all three of these do really come across a lot, but definitely in these two, the top one and the bottom one, does come across a lot. 1 pound is 454 grams, and again, 1,000 grams in a kilogram, and there's about 2.2 pounds in a kilogram. They like to use both on weights. If you go to the gym or any lift, they got the pounds and the kilograms sort of on the weights and stuff like that. So let's talk a little bit about temperature. The temperature scales that we come across a lot in chemistry, frankly, are Celsius and Kelvin. So these are the two really main temperature scales that we come across. Degrees Celsius and Kelvin. There's really three types of temperature scales: degrees Fahrenheit, degrees Celsius, and Kelvin. So one of the main difference between those three is here we do not use any type of degrees. It is just stated as being Kelvin. So if you had like 454 Kelvin, that is how you would refer it. You wouldn't use the little degree sort of symbol. The Kelvin temperature scale, for the most part, is what everybody converts into. And going from Celsius to Kelvin is really a conversion we use a lot. I think we may see it a little bit later on, but I'll pop it up here just in the case we don't. The temperature in Kelvin is the temperature in Celsius plus 273. The actual proper number is 273.15. Most people don't use the 0.15 because it gets rounded off anyways. So I'm good with 273. Most people are good with 273. But you may occasionally see somebody write 273.15. And again, that really is the true value, but most people kind of round that off anyways, as it will get rounded off. That obviously means as well, if we want to go from Kelvin back to Celsius, the temperature in Celsius would be temperature in Kelvin minus a 273. So that would be how you would go backwards. I would say definitely here, this conversion used a lot. I would say for our purposes, when we get into the gas law, there's a lot formulas that involve temperature, and you're converting Celsius to temperature. I'll put the other conversions up here, and again, I think there might be another slide, so I might be jumping the gun here, but we'll just do it anyways here. If you have you want degree temperature in Fahrenheit, that is 1.8 times the temperature in Celsius plus a 32. And if you want the temperature in Celsius, that would be the temperature in Fahrenheit minus 32 divided by 1. I can get it right. It's 1.8. Now, the 1.8 is maybe something you might have learned as well when we were younger. It's like 9/5, like a fraction type of deal. So it's the same idea. I would say probably outside of chapter 2, you probably won't see Fahrenheit anywhere. And most of the time, you'll be doing the Celsius to sort of Kelvin conversion. The differences between really boiling point and freezing point, water freezes at 0 degrees Celsius and 32 degrees Fahrenheit, and water boils at 100 degrees Celsius and 212 degrees Fahrenheit, and water freezes at 0 Kelvin, and which would be 0 Kelvin, sorry, and 273 or 373 Kelvin for our boiling point there. 1.80, the one on the bottom? Yeah, it's 1.80. Other questions? So the SI, and I think we'll get back to the temperature conversions. I think I might have just jumped a little ahead there. But the time is really seconds is commonly what we use. If you think about a lot of times, if you maybe do an experiment or something like that, you're probably not going to sit there for days or weeks or things like that, or years. Maybe you will, but most of the time, if you do something, it's sort of seconds is a very common one. Just a reminder, right? There are in 1 minute, how many seconds? There you go. And in 1 hour, there are how many minutes? Let's see, right? And in 1 day, there are how many hours? There are 24 hours, yeah. All right. Not 60. It's very common. People go like 60 seconds, 60 minutes, 60 hours per day. Nobody wants that. So keep that in mind. Common ones there. All right. All right, so let's look at each of these here. For each of the following, indicate whether it describes length, mass, or volume. So why don't you take a moment or two and determine what we're talking about here. So on the first one here, we got kilograms. So kilograms is a unit of, should be mass. Yep. We have meters, which is a unit of length. All right. Grams is a unit of mass. And lastly here, we have liters, which is a unit of volume, right? So again, it's very common people maybe don't understand what units sort of represent what type of measurement. So it's really important, again, as I mentioned, that you have that understanding of, you know, what they represent. All right, so the SI unit for each of these, we kind of went over meters cubed there for our volume, kilograms, meters for our SI unit of length, and temperatures are Kelvin. And again, we may not always use those units, but they're sort of the standardized units or standard unit for that type of measurement. Like I mentioned before, a lot of times for mass, we will use grams. A lot of times for like length, centimeters is used a lot, you know, millimeters, kilometers, you know, sometimes use those guys as well. And definitely for volume, things like cubic centimeters or milliliters is used a lot. All right, so we're looking for our SI unit here. So we're looking at height, which is really a length measurement. Which one of these should be the SI unit? Should be 3, right? Meters would be the SI unit. Feet and yard would be more of an English sort of unit is there. The mass here would be kilograms, right? Again, these are mass measurements, but they're more on the English sort of system of units. And temperature here, the SI unit should be should be the Kelvin there. Again, degrees Celsius and degrees Fahrenheit are obviously temperature values, but sort of the SI standard unit there should be Kelvin. Any questions on any of those there? All right. So let's talk about measured numbers and significant figures. There's really two types of numbers that we come across in chemistry, and we're going to talk about a little bit of both of them and sort of the deals with each of them. But there's really two types. There is a measured value, which pretty much like it sounds like, you take some type of measurement to get there. So that's some type of measurement. And there are kind of exact numbers, which are not based on measurements. They're based on one of two things. They're based on something that is counted. So for example, if I had all of these pens here on my desk, I'm not going to do some type of experiment to figure out how many pens I have. I'm just going to simply count how many pens I have. The classic example is like if you had a basket of apples, you would just simply count how many apples there were in the basket. Again, not do some experiment to figure out how many you have. The other way, and probably the more ways that we will kind of commonly see exact numbers, is also what are sometimes referred to as definitions or equalities. And these are things like we kind of saw earlier a little bit, 12 inches is 1 foot. So this is what is considered sort of an equality or a definition, and it's also considered an exact number. As we'll talk about, what exact numbers are essentially numbers that can have unlimited amount of significant figures. And why they are important is when we are doing calculations that involve exact numbers, because they pretty much could have as many significant figures as you like, we pretty much just sort of ignore them in the calculation in terms of how many significant figures our answer should have. We're going to go through that here in this chapter. And that's because I could say, well, I want to give it like 4 significant figures, and you would go, well, I want to give it like 6 because it could have as many as I want. So there's a lot of like people may give different amounts of significant figures to those numbers. So we sort of ignore them in terms of calculations, and they really don't play into calculations because of that. So it's really the measured numbers that really play into what are known as significant figures, and really, when we do calculations, how far we should take those calculations. Now, whenever we take a measurement, there is always some degree of uncertainty. So there's always some degree of uncertainty no matter who takes a measurement. And the degree of uncertainty really is determined by the actual piece of equipment that you use. So for example, if we take something like this, and we want to, again, take maybe a reading here, we'll go like to here-ish. There's really always what you want to do when you take a reading is you want to figure out really what the scale on the piece of equipment you're using represents. So basically, how far can you take that reading properly? And that usually involves you finding 2 things on the scale. One is sometimes referred to as the larger markings or bigger markings. So in this particular case, the big marking here is 1 centimeter and 2 centimeters. So the difference between that is basically 1 centimeter. You also want to look at the smaller markings, and you want to figure out what the smaller markings represent. And to do that, what we really want to do is count up how many of the smaller markings there are between kind of the big marking. To do that, typically we start counting actually after the last big marking. So once again, here we would count here, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings until we get to the next biggest marking there. So there are 10 markings, and the difference between the two biggest markings is 1 centimeter. That means each of the smallest markings in this case represents 0.1 centimeters, basically. If you're not sure, just take 1 divided by 10, and that will give you 0.1 centimeters. That means that this marking here would be 1.1, this would be 1.2, 1.3, 1.4, 1.5, and so forth, all the way across there until we get to basically 2. Now, when we look at whatever we're trying to measure, no matter sort of what piece of equipment you use, there always should be some numbers that frankly everybody should agree upon. So when everybody looks at this, everybody should agree upon it is at least 1.2 in this case. And we would want to record always all the certain numbers. So in this case, we would record 1.2. These are what are sometimes referred to as our certain numbers. But if we look at that line there, it's not exactly on the 1.2, it's not exactly on the 1.3. So this is where sort of the estimation comes into play when we're taking a reading. I may look at it and go, well, it's kind of closer to the 1.2 than maybe the 1.5 or even halfway there. And I may say, well, I think it's maybe like 3, for example. And I would record 3 and then obviously the units with it. Somebody else may look at it and go, well, I think it's already kind of closer to half, so maybe they record a 5 or something like that. So what I just recorded was sometimes referred to as the first uncertain number, or sometimes referred to as the estimated digit. And whenever you take a measurement, it is always customary to record all of the certain numbers plus the very first uncertain number. And really, that is for the most part what we like to call significant figures. So when you record all of the certain numbers plus the first uncertain number, that is what is referred to as significant figures. That means in this case, this number would have how many significant figures? It would have 3 significant figures in this case, where the uncertainty would lie in that 3 at the end of the number in this case. And it's basically saying, I think it's 1.23, but maybe it's like 1.22, maybe it's like 1.24, somewhere in that ballpark is where the measurement would be. Any questions on that there? Now, when we look at an equipment like this, we could also figure out what is sometimes referred to as sort of the precision of this piece of equipment. Basically, will tell you how far you could take this reading to. And you could do that by taking the smallest marking and dividing it by 2. So if I take 0.1 centimeters and I divide it by 2, that basically means I could take this reading to plus or minus really 0.05 centimeters. So really, this could be written 1.23 centimeters plus or minus 0.05 centimeters. I personally don't need you to do that, but some people will do that. But what it really will tell you is we could take it there to the second decimal place, and that's exactly where we took our reading to, and that's how far we really should take the reading to. So if you're ever not really sure how far you could take that reading to, if you could figure out what each of the smallest markings represent and divide it by 2, that is how far you should take the reading to. It will kind of tell you that. Any questions on that there? By the way, speaking of taking measurements and significant figures, there is a difference between 2 words that are sometimes commonly used together, and that is accuracy and precision. Accuracy, or being accurate, is how close a number is to the true value. while precision, or how precise a set of measurements are how close a set of numbers are to one another. So what is the difference between that? Accuracy basically means if you're really accurate, you got really what the right answer should be. Precision simply means, in terms of experiments, is a lot of times in experiments you do multiple trials of the same sort of experiment, and that basically will tell you how reproducible your experiment is. If you have very high precision, that means you can reproduce your results multiple times in an experiment. So a simple way would be to explain it would be sort of a bullseye, right? If you throw in darts, the goal of throwing darts, right, is to hit the bullseye in the middle. So if I take my darts and I throw them, and at the board here, I hit here, I hit here, I kind of missed the board completely over there. Am I very accurate? I am not, right? Because the goal here is to hit right there in the middle. Am I very precise? I am not very precise because I have one that's not even near the others, right? It missed the board completely. So I'm neither precise here nor accurate. If I then pick up my darts and not hit that button, oops, try that again. I think I just erased all that, huh? So let me just drop that back in. You know, redraw my dartboard because I apparently erased it. All right, I pick up my darts and find a new dartboard, and I throw my darts and I go boom, boom, boom. Am I accurate? I am not accurate because, again, we're shooting for the middle, right? Am I precise? I am precise. I'm precisely not accurate, right? Which means you could absolutely do something the exact same way multiple times, like an experiment, and do it wrong every single time, but you did it wrong every single time the exact same way. You could get the same result, but it may not be very accurate or what you're going for. So you can be very precise, but not very accurate, which again is probably not what you're shooting for if you're doing some type of experiment. So here we'll pick up our darts here, hopefully not erase the entire board. And we'll throw our darts one more time here. Am I accurate in this case? Am I precise? Yes. And that's, you know, hopefully, I'll spit that out, that word, whatever word I'm thinking of there. That is ultimately what you want to do when you do experiments is you want to be very accurate, right? And you also want to be very precise. So you want to do the experiment right. And you also want to do the experiment where it can be repeated multiple times, right? And produce the same results. And that's sort of the goal of those two things. Any questions on the difference between accuracy and precision? So continuing on with our measurements here, let's say we had here, we'll graduate cylinder here. And again, we're going to put our liquid in there, which, as we talked a little bit earlier, we'll do a little curvature, right, which is our meniscus. And once again, here we would want to look at this chart and look at our big markings, which once again is going to be, in this actual case, 10 milliliters difference between the two big markings, between this marking and this marking. We will count up how many of the smaller markings we got going on, starting with, once again, past that big marking. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I got 10 of the smaller now green markings here. That means each small marking is how much? Each small marking in this case, 10 divided by 10 is 1 milliliter, right? This guy would be 11, that would be 12, that would be 13, that would be 14, that would be 15, and so forth, all the way up till you get to 20 in this case. We'll put 16 there. So once again, when we look at this, we would want to find the numbers that everybody should agree upon. And in this case, no matter who takes a peek, should hopefully agree. that it is at least 15. And again, those would be our certain numbers. When we look at it here, going again from the bottom of the meniscus, which sometimes is easier to see. Sometimes it's not that easy to see. We could see that we're not exactly at 15, but maybe in this case, you do look at it and go, I think it's like halfway between the two numbers. So maybe you record it as 15.5 milliliters. This would have how many significant figures in this case? Would have 3 significant figures, with the 15 here being our certain numbers and our 5 being our first uncertain number, or our estimated digit in this particular case. Once again, if you wanted to really figure out how far you could take the reading, you could take your smallest marking, which is 1 milliliter, divided by 2. Tells you this is plus or minus 0.5 milliliters, which is 1 decimal place, which is exactly where we took the reading to. So again, that is how you can figure out how far you can take the reading. Typically speaking, you could go one more place, usually to the right of the smallest marking. Not always, but typically speaking, you could go one more place to the right of that smallest marking. Any questions on that there? So let's take a look at maybe an example where you wouldn't necessarily be able to do that. Let's say we had some random lines here. Let's say we got, call that 80. Call that 90 milliliters. And let's put it right about there, right? All right, in this particular case, our big markings, the difference between our big markings is how much? It is 10 milliliters, right? Between 80 and 90 is 10 milliliters. And if we count up our markings between those two, starting right here, that is 1 small marking, that is 2 small markings, that is 3 small markings, that is 4 small markings, and that is 5 small markings. In this case, each of the smallest markings represent how much? Each of the smallest markings here, 10 divided by 5 is 2 milliliters. Yeah, so each of the smallest markings represent 2 milliliters. That would be like 82, that would be 84, that would be 86. That would be 88, and the next marking would be 90 in this particular case. Now, if I find myself right about there, what is between 86 and 88? It is 87 milliliters. This would have how many significant figures? It would have 2 significant figures. The uncertain number would be which one? It would be 7 would be your estimated digit, or your uncertain digit. And that is because between 86 and 88, there's not enough room for you to go 86 starts and ends here, and like 87 begins and ends here. There's not enough room to figure all that out. So the best that you could do is take it really to the ones place. I could figure that out as well to confirm by taking my smallest markings once again and dividing by 2 tells me plus or minus 1 milliliter is basically where I could take that to, and that's exactly where I took the reading to. So I would say 9 times out of 10 you could go one more place to the right of the smallest marking, but not always. So it's really important to make sure that you do look at the piece of equipment and take the reading accordingly. Any questions on that there? Now, in general, a couple other lab type equipment that we sometimes come across, for example, anything that's a volumetric glassware. Volumetric glassware basically has 1 marking on it, and that marking is the volume. So a volumetric flask, for example, looks something like this, and it's got like 1 marking. And if this was like 100 milliliters, this marking would represent 100 milliliters, and typically we take it to 2 decimal places. There's also a volumetric pipet, which kind of looks like this, kind of comes out on the sides and then gets a little bit narrow. Also has one marking only, and anything that's volumetric, by the way, means expensive. It has one marking. Don't break it. And in this case, say if this was 25 milliliter, we would take it to 2 decimal places. So if you have anything that's a volumetric sort of glassware, it is typically always taken to 2 decimal places. It has usually just one marking. That's it, and that's all there is on there. There are sometimes things like what are known as Burettes, which actually sort of looks something-ish like that. This is the was referred to as a stopcock. That is what opens and shuts it. Basically, it's a little turner thing. But different is actually the scalding on something like this, which is a burette. And that is, we actually fill it from the top, but it drops out the bottom. And what that means is when we go to the top, it's actually 0 here. And it's 1, and it's 2, and it's 3. It actually gets larger as you go down from the top rather than the opposite. It gets larger as you go from the bottom up on most pieces of equipment. So that means if you found yourself somewhere in this region, this actually would be 1 point something, not 2 point something. Again, it would be filled from the top and increase as you go down. So that's the one common piece of lab equipment. Sometimes you come across, by the way, I won't make the markings here, but there usually are 10 markings between each of these. And usually you could take the reading to 2 decimal places is typically where you can take those readings on a burette. So that's one piece of glassware that sometimes is a little odd for people to read because 0's at the top and it actually increases as you go down. Sometimes people mistakenly, when they use something like that, will fill it to the top at 0 and go, if it's like 25 milliliters total, they'll go 25 milliliters at top and kind of record it that way. And you actually will record everything incorrectly. So it's really important to make sure that you read things correctly and record things properly. Any questions on that there? Now, it's also really important that you record to the right number of digits. So we go back here, let's go use our same sort of ruler move here. Now let's say we were sort of measuring something that is like exactly on the line there. So this is the same ruler setup that we used earlier, where the big difference there was 1 centimeter. The smallest markings are 10 markings between them, which meant each one, again, just like we talked about earlier, was 0.1 centimeters. So everybody that looks at this will go, this is 1.1, 1.2, 1.3, 1.4. So you feel it's exactly on 1.3 in this case. Do I record 1.3 centimeters? Do I record 1.30 centimeters? Is there a difference between those 2 measurements? The answer is there actually is a difference between the 2 measurements. So let's just analyze this really quick to see that major difference. So when I look at this measurement here, how many significant figures would this guy have? It would have 2 significant figures, where the uncertain digit would be the 3 in this case. So with that measurement, what you're saying is, I think it's like 1.3 centimeters, but maybe it's like 1.4 centimeters, or maybe it's as low as like 1.2 centimeters. So that's where the error is there in that first decimal place. And clearly, if we look at it here, it's really kind of like nowhere near those numbers, right? That's a lot of extra error that you kind of threw in there by lofting off the 0 in this case. So you actually would not want to do that, because as we talked about before, with this piece of equipment, you pretty much could take the reading to the 2nd decimal place, right? And that means that we would want to do this guy, which has how many significant figures? 3. The uncertain number here would actually be the 0, right? And basically what that says is, I think it's 1.30, but maybe it's like 1.31 centimeters. maybe it's 1.29, which is pretty much what we are seeing on this particular scale. So it's really important. It's a mistake that a lot of people make, which is it's right on the number. I'm just going to record what the number says. But if that piece of equipment has the ability, like it does in this example, to actually go to the second decimal place, you need to maintain that by putting a 0 there. Otherwise, if you get rid of that 0, A, technically it's wrong, and B, you made your measurement a heck of a lot worse than it should be. You created a lot more error. There's a lot bigger error difference, right, between 1.3 and 1.4 and 1.2 than there is going one more place to the right, where the difference is at 0.01, right, difference. So there's a lot more error that you created by just lofting off that number. So it's really important, even if it's like you feel it's dead on a number, you should record the number that's there, but also maintain the correct number of decimal places with zeros to maintain really the precision, the correct sort of reading on that particular equipment. Any questions on that there? So here, if we look at this, our big units here are basically 1 centimeter. Our small units here are also 1 centimeter, right? There's no other dashes anywhere in there, which means that we could look at this and record it to 4.5 centimeters probably. Again, it's at least 4, not exactly 5. My smallest marking is actually 1 milliliter. I can divide it by 2, which tells me I could take it to the first decimal place, which is what we should do here. Uncertain number would be right there. Certain number would be there. And this would have how many significant figures? 2 significant figures in this case. Any questions on that there? All right, so that is exactly what they agree. So that's good. Now, when we look at this guy here, once again, if we look at this scale, we got 4 and 5. So the difference here is our 1 centimeter. There is, again, if we count up all the little markings, 10 markings, which is our same 0.1 centimeter. So once again, if we took our 0.1 centimeter and divided by 2, tells us plus or minus 0.5 centimeters, which basically means we could go to the second decimal place. So this is at least 4.5 here, which is this mark right here, 4.5. Again, it looks like it's just a hair over that. So we would want to record 4.55 centimeters in this case, which has 3 significant figures. We again would not want to record just 4.5 because that would have only 2 significant figures, and you have the ability to go to one more place to the right. Any questions on that there? All right. So same idea here. In this case, we are kind of dead on our 3 mark. And as we talked about before, our big and small markings in this case is 1 milliliter. So that means we could actually take it to the first decimal place, right? One more place to the right of the smallest marking. Once again, here, we do want to maintain that spot with the 3.0. The uncertain number here would be the 0. If I just recorded 3 centimeters, how many significant figures would that number have? That number would have 1. There's only 1 number, so that's got to be the answer, I think, in that case, right? That means the uncertain number actually is which number? It is a 3, which means you're basically saying, I think it's 3, but it could be 4, it could be 2. And once again, if you look at that actual scale there, it's like nowhere near those numbers, right? So we would not want to just record the number because it's there on the line. We've got to maintain, what we are taking our readings of. By the way, speaking of rulers, right? Up on top, you have like inches, right? On a lot of rulers. On the bottom, you have a bunch of little markings and some big markings. And on the bottom, the big markings are centimeters, right? And the little markings on the bottom are millimeters, right? So in a normal ruler, up on top are inches, bottom centimeters. The bigger numbers, the little guys, are millimeters. there's 10 millimeters in a centimeter. So the little markings are the millimeters on a real ruler. All right, let's take a reading of that, see what you come up with. Hopefully it's on there and nothing moved. Hopefully that is right. All right, so wherever that red guy is, we'll take a reading. So, obviously the big markings here, that's like 9, that's like 10. So big markings here is 1 centimeter. Once again, if we count up the little markings we got going on there, that is 1 marking, 2 markings, 3 markings, 4 markings, 5 markings, 6, 7, 8, 9, and 10 markings. So we do have 10 markings between them, which, much like our other examples, means that each of the smallest markings is 0.1 centimeters. We typically could go one more place to the right, right? Now, everybody might agree that it is like dead on, perhaps that dot right there, which is our 9.2 centimeters, which would be our exact numbers, but we should also record what with it? We should record the 0 here in this particular case. Again, we have the ability to do so, and that means that the uncertainty here is in which digit? Is in the 0, right? And it has how many significant figures? It has 3 significant figures in this particular case. So it would be number or letter 3 there, or number 3. Any questions on that one? All right. So let's talk about significant figures and taking and really counting significant figures. So as we just mentioned, pretty much any type of measured number, all the values that you see there should be significant. And that's because you should always, if you take a measurement correctly, record all the certain numbers plus that very first uncertain number. And those would be your significant figures. By the way, the estimated digit is not always the last number that is written, but it should be the last significant figure that is in the number. So that is a distinction, by the way. A lot of cases, it is the last number written, but it won't always be the last number written. But the right definition is it is the last significant figure that there is in that particular measurement or number. All non-zeros are significant. So all non-zero numbers are significant. And that, frankly, is where you start counting. You go left to right. And as soon as you hit the very first non-zero, that is where you should start counting your significant figures. And it is zeros that sometimes can be significant, sometimes they're not. So let's talk officially about sort of each of these here. Let's start with the non-zero numbers. Any non-zero number is always going to be significant. So if you had 3, 2, 5, 6, we would start left to right, and we would start counting right there since that is our very first non-zero number. Obviously, all the rest of them are non-zeros as well. So this would be 4 significant figures in this case. Now, when we get to zeros, there actually are 3 different types of zeros. There is what is sometimes referred to as the leading zero. And the leading zero are not significant. They're sort of like placeholders. So if you had something like 0.003245, starting left to right, all these zeros here are not going to be significant. We do not start counting until we hit that first non-zero number, which is the 3. The 2, 4, 5, and 6 would all be non-zero, so they would be significant. So that is going to give us, looks like 5 significant figures in that particular case. Any questions on that there? The next type of zero that we come across is what is sometimes referred to as a captive zero or a trapped zero. And those guys are significant. So any zero that's really trapped between 2 non-zero numbers will be significant. So if we had 30005, once again, we would start counting here at the 3. And all these zeros are trapped between non-zero numbers, so they're significant. And then our 5 obviously is a non-zero at the end, so that would be significant as well. That looks like 5 significant figures in this case. Questions on that there? Now, the 0 that I think gives people the hardest problem is what is sometimes referred to as the trailing 0. These are the zeros at the end. And the trailing 0 may or may not be significant. And what determines whether or not the zeros at the end are significant is they will be significant if there is a decimal place. In the number. So if there's a decimal point really anywhere in the number, really decimal point anywhere in the number, that will make every single 0 that comes at the end significant. If there is no decimal point in the number, then it would not be significant in that particular case. So if I had 6,000 written like this would have how many significant figures? It would have 1. It would just be this one. All the zeros at the end are not going to be significant because there's no decimal point there. So this would have 1 significant figure. This means that the uncertain number is actually which number? It is actually the 6 in this case, not the last number written. That is the last and only significant figure. And that would actually be where the estimated digit or uncertain digit would be. So that was what I was saying a second ago. Not always is it the last number written. Like in the lab question, 12,000 with no decimal. It's actually the 2, not the 0 at the end of that one. Again, because there's only 2 significant figures. So you want to make sure it's the last significant figures where that estimated digit would be. If I laid up like a 6,000 and we'll just throw a decimal right there. How many significant figures would that have? It would have 4 significant figures with that decimal there. All these would then turn into being significant. And if this was some type of measurement, the estimated digit in this case would be which one? It would be the last 0 in this case, would be your estimated digit. So 9 times out of 10, it really is a lot of times the last number written, but it's more important to remember it correctly, which is it is the last significant figure that is written, like the case up there. Question on that there. We also talked about exact numbers that they could have an unlimited number of significant figures. So we'll talk about that in just a second in terms of calculation. But we also talked about scientific notation and a reminder that if you write a number in scientific notation or have a number that's written in scientific notation, all of the numbers before the times 10 part are significant. So all the numbers that you have before the times 10 part are significant, which means this guy would have 3 significant figures. Sometimes scientific notation is the only way to get the right number of significant figures, is to actually write it in scientific notation. And that is because you can control how many significant figures you need. For example, if you just needed 2 significant figures, you could write 4.3 times 10 to the 3, and now this number would have 2 significant figures. So whenever you write a number in scientific notation, all the numbers before the times 10 part are always significant. And it's important to understand that. It's also important to understand that if you do have a number in scientific notation, let's go with 2.70 times 10 to the 2, for example, that you should assign significant figures based on the way the number is written there. It is a very common mistake that people will do is, I'm going to turn that into a decimal. And they'll turn this into a decimal and go 270. And they'll go, oh, that has 2 significant figures, which it does the way it's written. But our original number actually has how many significant figures? 3. So you shouldn't do that. It's a very common thing that people do. They take the numbers in scientific notation, they convert it out into a decimal form and then assign the significant figures. But the purpose of it being written in scientific notation is to indicate a certain number of significant figures. So you should assign the significant figures based off of the scientific notation. By the way, when you go from scientific notation to decimal, or decimal back to scientific notation, you should never ever lose significant figures. So for example, if I really was to do this correctly, I should not write it like that, but I should perhaps write it like this, which would then have how many significant figures? Would have 3 significant figures, right? That would have 3 significant figures. This guy has 3 significant figures. That is the correct way to bounce back and forth between those two. You shouldn't lose significant figures just changing it from decimal form to scientific notation or scientific notation to decimal form. Any questions on significant figures, on how to assign them? Now, important as well is, we'll talk about it now, I think, is actually doing calculations involving significant figures. So when we do calculations that involve significant figures, there's really kind of 2 types of calculations that we do. We multiply and divide, or we add and subtract, or subtract. When we multiply and divide, the answer should have the same number of significant figures as the number with the least number of sig figs. So when you multiply and divide, you're looking at all the numbers, you're either multiplying or dividing, and you're looking to see which of those numbers has the least amount of significant figures. And that's the exact same amount of significant figures your answer should end up with. So for example, here, if I did a little 325 times 1, 2, grab my calculator here, 325 times 12 gives me 3900 in this case. I am multiplying, which means I'm looking at significant figures. This has 3 significant figures. This has 2 significant figures, which means my answer should end up with 2 significant figures, which I actually hit there by accident, just making up those numbers. So that written like that is 3900. If I put a decimal point at the end to make it look more scientific-y, that could be a word. It might be a word. How many significant figures would it have? 4. So sometimes putting a decimal is not really what you want to do in certain situations, right? Because then you would have the wrong number of significant figures. I could also, if I wanted to, lay up a little scientific notation action. 3.9 times 10 to the 3 would also be another way that I could write it with 2 significant figures. Any questions on that there? What's up? Yes. So we got, we'll do 1, 2, 4, 5. We'll divide it by 3, 2, 3. So if we take 1245 and we divide it by 3, 2, 3, we end up with a number here. We end up with 3.854489164. Too many numbers. Don't write that many numbers. Yeah. So that clearly is way too many numbers, right? So we are dividing. So we want to look at significant figures of our numbers we just divided. So the very first number here has how many significant figures? 4. The number we divided by has, the one with the least number of significant figures is 3, which means our answer should actually end up at 3 significant figures, which takes us to here. And the right answer should be 3.85. 3 significant figure. Question on that? Now, when we add and subtract, it is a little different. We are not looking at significant figures, but we're actually looking at decimal places. So the answer should have the same number of decimal places as the number with the least number of decimal places. So when you transition to adding and subtracting, you're no longer looking at how many significant figures, but you're frankly looking at how many decimal places in each number. And it is the least number of decimal places. So if we did something like some adding here, let's go with this. We'll do 4.323 plus 1.44 plus 2.0. And give it the old college try here without a calculator. So that's going to be a 3. That might be a 6. That could be a 7. That might be a 7 as well. So that's what we would get, hopefully, if we added it together in this particular case. Once again, here we are not looking at significant figures, but decimal places, which means when we analyze the 3 numbers in this case that we added, this guy's got 3 decimal places, this guy's got 2 decimal places, and this guy's got 1 decimal place. That means my answer should end up at how many decimal places? Should end up at 1 decimal place, which is right there, yes? When I round, though, right, I do want to look at the number to the right. And should I round up? Should I drop the numbers? We should round up in this case, right? The number is a 6, so we should end up with 7.8 as our answer. 7.8 has 1 decimal place, but how many significant figures does it have? It does have 2, and that's important because if you take that 7.8 and continue on with another calculation, you might need to look at sig figs, right? If you take in multiply or divide. So it's important to keep those things straight. The reason it is the least in each of those, it is the least number of significant figures when we multiply and divide. It's the least number of decimal places when we add and subtract. That is because the least number in each of those cases, frankly, are your worst measurement. So your calculation is only as good as your worst measurement. So your least in each of those would give you kind of your worst measurement, and that would give you basically how good of a calculation you kind of did there. Any questions on that there? Now, if we kind of did multiple things together, we do want to kind of keep track of stuff. So for example, let's just say we had some fun here. We took some 32.356 and we added 1.2, then we divided by 4, 5, 6, 7. I am just making up numbers in a row, apparently. And while we're at it, why not? Let us then subtract. I'm going to hope for the best here. That's probably not going to work. Let's subtract. Actually, let's add so we won't run into trouble. Let's add 1.436 to it. All right, you give it a go. I will as well because I just made it up. We'll hope for the best there. Okay, let's take a look. Yeah. So if we approach something like this, by the way, mathematical rules of operation, whatever they call that these days, where should I begin really? I should begin in the parentheses, right? And then I should then divide and then add at the end, right? So that's sort of the order of operation. Parentheses first and take care of the dividing part there and then add it to the end. That means in the parentheses, I'm really adding, right? Which means I should be looking at significant figures or decimal places. Should be looking at decimal places, which means if I did add that number up on top, by the way, I would have 33.556. Again, not concerned right now with anything else, but that would be the number I get. I should be looking at decimal places, which means really at this point, that top number should end up at how many decimal places? Should really end right about there. Yeah, that's really where it should end. And actually should be rounded up to about 33.6. Now, you may want to actually round the number at this point, or you may not want to round a number. In general, if it's maybe not a straight sig fig problem like this, but you're doing conversions and stuff like that, typically you want to wait to round to kind of the end, but you do want to kind of keep track of everything. In this case, I think you'll get pretty close to the same answer if you rounded right at this point, or you kind of waited to the end to round. So the next sort of operation we would do, right, is we would then take that top number and we would divide it here by the bottom number. So once again, here we are dividing. So I'm going to look at sig figs or decimal places. I'm going to be looking at this point at significant figures. And that's why it's important to remember that this really should be 33.6, right? That has how many significant figures? 3. That you're then going to divide by this number on the bottom, which has 4 significant figures, right? Which means my answer for the division part should end up with how many significant figures? Should end up with 3. Once again, not decimal places, but sig figs we should end up with. So let's just say I rounded and went 33.6 up on top, divided by 4, 5, 6, 7. On the bottom here are what I would get is 0.007357127, which the last thing here I would do is add. But before I do that, again, we want to kind of keep track of what we're doing. So we just said we should end up with 3 significant figures, which would take me to which number here? It would take me to the 5 here, right? And again, once again, we would technically round up at that point. And that's important because the last thing I'm doing here is actually adding. So if you wanted to, we could round it up here and we would actually be taking 0.00736, right, on the round, plus 1.436. Last step I'm doing here is adding as well, right? So again, we're going to be looking at decimal places. So we have basically 5 decimal places, right? And we have 3 decimal places, which means my final answer should have how many decimal places? Should have 3, right? So if I take that 0.00736 plus 1.436, you will get 1.443 as your final answer there, which has 3 decimal places, but how many significant figures? It has 4 significant figures, right? Where the uncertain number actually would be the 3. So this is a lot of different combinations of stuff that's going on. You could either round or you could wait to round to the end, which I think you get pretty close to that number, maybe slightly off depending. But you do want to kind of keep track. So here I highlighted things as I went through it to know kind of where I should end up. And that's a good way. Again, really the good way is to wait to the end to clean it up, but you should still focus in on all the calculations that you do. You know, should you be looking at sig fig? Should you be looking at decimal places and really how far you can take the reading? The ultimate goal at the end is really your last calculation tells you kind of where you should clean it up to. As in this case, we added. So we were looking at decimal places. If this was different and we multiplied at the end, we would then look at sig figs, right? Which might give us a different sort of final answer. So if you're doing multiple calculations along the way, the safe move really is not to round so much till the end and then sort of clean it up at the end. But you do need to kind of keep track of everything that you're doing. And, you know, that's how we get to sort of the correct significant figure at the end. Any questions on that one there? Last thing here is rounding. Speaking of rounding, as I mentioned, you should kind of wait to the end to round, especially if we're going to take that number and continue on. Because the reason is if you round a little bit every single time and you take that number, do a calculation round, do a calculation round, you really will be moving yourself further and further away from the right answer. Normal rounding rules apply. So once again, if it is less than 5, you're just going to drop the number to wherever you want to end up next to it. If the number next to where you want to end up is 5 or more, you round up. And no craziness in terms of, you know, rounding. You know, if you have 13,333 and we're shooting for our 2 sig figs here, once again, that would take us to here. And the correct answer is 13,000 because that has 2 significant figures and still means basically the exact same thing. Sometimes people are so focused on the significant figures, they just go for it no matter what and go, 13 is 2 significant figures, which it clearly is. But there is a very, very big difference between 13,333 and 13 in terms of the meaning. So you never want to round where you actually change the meaning of the number. And like I said, there is occasionally kind of only one way sometimes to get a number to the right number of significant figures. So if you find a way like, hey, I got to get this guy to the proper number of significant figures, and I can't do it like in decimal form, then probably significant figures is your best way to write that number to get it into probably the right number of significant figures. All right, any questions on sig figs and measurements, calculations involving significant figures? Any questions on any of that stuff? Okay, we will lay it up there for today.